In today's video, we shall take a closer look at force and motion. So let's begin with motion. As we have seen before, motion of an object can be described by two quantities. The first is the velocity, and followed by the acceleration. Acceleration is a measure of the change of velocity with respect to time. And these two quantities are vectors. An important quantity that is deeply related to velocity and acceleration is force. It is also a vector, and it's quantified in the units of newtons. As we shall see, velocity and acceleration are dependent on force, in a sense that the force controls velocity and acceleration. Let's see how this is the case. Assume that you have an object, and this object is moving along a straight line, like that. Let's assume it is moving with a constant velocity. So the velocity has the same direction all the time with the same magnitude. What that means is, as the object moves to the right, it will cover an equal distance in equal amount of time. Let's call that t. And this continues forever. What do we mean by that? Since the magnitude of this velocity here is given by that distance covered over that time interval, to have different value for v, d must be different for the same time interval. For example, if initially 2 meters of distance is covered, let's say in 1 second, and now the object moves only 1 meter in 1 second. What that means is the v new is 1 meter per second compared to v old, which is 2 meters per second. In this case, the object has slowed down. Or let's say initially the object was covering 2 meters per second, and then now it speeds up in such a way now the object is covering 3 meters in 1 second. So in this case, the new speed would be 3 meters per second. When that happens, the velocity is no longer constant. You see, when the velocity changes, for example, from 2 meters per second to 3 meters per second, that suggests the presence of acceleration. When acceleration is present, or when the object is accelerating, we cannot say that the object will move with constant velocity forever, such as here. When the object is accelerating, something must be causing that acceleration, and that something is what we call force. So let's look back at this example. Assume that initially this object is moving with constant velocity, say 2 meters per second I hat. It will keep on moving with such a velocity forever unless it starts to accelerate or start to decelerate. In other words, it will keep on moving with that velocity 2 meters per second forever unless there is a force acts on it. This very statement is Newton's first law of motion. If this force starts to act in the same direction as the direction of that initial motion, the velocity will increase to something greater than 2. If the force starts to act in a direction opposite to that of motion, then the velocity will decrease to a value less than 2. So that is the essence of Newton's first law of motion. An object will be moving with a constant velocity forever unless there is a force acts on it. So now we know there is a connection between force and acceleration. So we say the acceleration is linearly proportional to that force. So that means the force equals a constant times that very acceleration. So this constant is the constant of proportionality. In this case, that constant is simply the mass of the object in question. So if you have a mass, let's say 1 kg, and a force of 2 Newton acts on it, then the acceleration A is quite simply 2 over 1, which is 2 meters per second squared. Likewise, if you have a higher force that is acting on the same object, then the acceleration will be 4 over 1, which is 4 meters per second squared. So you see, acceleration is proportional to the force that is acting on the object. And if I were to change the mass of the object to, let's say, 2 kg, then in this case, the acceleration will be 4 over 2, or 2 meters per second squared. And that is the role mass plays in this equation as the constant of proportionality. We see that the effect of mass is that the higher the mass, the harder for that object to change its velocity, namely the acceleration goes down. As we have seen in this example, when we transition from 1 kg object to 2 kg object, this effect is called the inertia effect, which is a measure for an object to resist any change in motion. So when you have two objects, let's say 2 kg and 1 kg respectively, the 2 kg object would have a greater inertia effect compared to the 1 kg object. What that means is it would be harder to move this object from stationary compared to that object. Likewise, it would be harder to stop this object while it's moving compared to that object. This equation right there is known as Newton's second law of motion. If an object is being acted upon by, let's say, 3 forces, like that. So this is F1, F2, and F3. Then the left-hand side of Newton's second law would read net force on that object equals mass times the object's acceleration. So in this example, the net force acting on this object is quite simply F1 plus F2 minus F3, judging from the direction. So if you want to include vector notation, then this simply becomes like that. Now let's look at Newton's third law of motion. Assume that we have 2 objects touching each other, so they are in contact like that. So let's call this object A and that one is B. There is a contact force at the point of contact. As a whole, they are not moving, so they are pushing each other, however. So the force on A due to B, it's going like that. So the force on A due to B. The force on B due to A will go like that. So force on B due to A. The magnitude is the same, but the direction are opposite. So we write the force on A due to B is minus the force on B due to A. Such a pair is called the action-reaction pair. So that means if a force, say FAB, acts on A due to B, then there is a force FBA on B due to A that obeys this equation. That is the essence behind Newton's third law. One other thing that we need to know about force is that it is a vector. So it has components. For example, if you have a body that is being acted upon by a force in that direction. So the force makes a direction theta with respect to horizontal. So you can take that to be the y-axis and that to be the x-axis. Let's assume the mass of the object is m. So the force has 2 components. The x component, which is given by the magnitude of that overall force times cosine of the angle between the force and the x-axis, and the y component, which is going upward. Likewise, it's given by the magnitude of the force times the sine of that very same angle. What that also means it has y component for the acceleration and x component for the acceleration. So we say Fx equals mass times ax, Fy equals mass times ay. So the object in general will be accelerating both along the x and y directions because there are forces along those two directions. Let's look at the following problem. In figure below, a 6 kg block A, that's this one, and 8 kg block B, that's that one, are connected by a string of negligible mass. So the string is there. Force Fa is 14 newtons acting rightward, that force, on block A, and force Fb is 28 newtons acting rightward on block B. We want to determine the tension in that string and also the acceleration of that system. So obviously the entire system will move rightward with some acceleration. Let's just look at object A first. What are the forces acting directly on A? Well, there are two. The first one is tension in the string, and the second one is Fa, which we know to be 14 newtons. Acceleration is that way. So that means there are two forces. The net force is tension plus 14. So the net force on A is 14 plus tension, and that must be the same as its mass, which is 6 times acceleration according to Newton's second law. So we have the first equation. 14 plus tension equals 6a, equation 1. Now let's look at object B. There is Fb, whose magnitude is 28 newtons, acting to the right. There is tension in the string that's trying to pull it leftward, and there is an acceleration a, the same acceleration. So the net force on object B is 28 minus tension, because this has got to be larger than that because acceleration is rightward. And that must be the same as the mass of a block B, which is 8 times acceleration, so Newton's second law. So we have the second equation, 28 minus tension equals 8a. So that is equation 2. There are two unknowns, t and a. Let's try to solve for them. When you take 1 and you add 2, the tension goes away. The left-hand side of 1 plus 2 is 28 plus 14. The right-hand side is 6 plus 8a, so that is 14a. So that means the acceleration is 3 meters per second squared. Now we can substitute this value for a either in equation 1 or 2 to get the value for tension. Let's do that using equation 1. So 14 plus tension is 6 times 3, because a is 3. So that means tension is 18 minus 14, which is 4 newtons. So that is the tension in the string connecting the two blocks. And that solves the problem. As always, thank you for watching.